example number 1, solving an equilibrium problem. So, yeah, write it up. The equation, example 1, asking the to find the force or tension applied to each rope that holding the box at at 3 different spots. So the rope just hang the box have equal the force. So net force on the box is 0. So in order to keep the box stationary, the rest at last. I mean, state at last. There should be some amount of force applied to the each rope. So there's no net force applied to the box. If the box experiences some amount of force, then the force produce the acceleration, then make the box actually moving downward or upward or any other direction. So in equilibrium, the box should stay at rest or the stationary state. So there's no movement, no motion. So we have to find what forces or tension need to be added into the rope. So we can solve the problem using the vectorial approach. So the weight of the box is 480 pounds. Weight of box 480 pounds, and the point equilibrium is S, that actually just keep the box floating on the air. So the location of the box is S, which is 0, 2, -1. And that rope S is supported by the 3 different plots, 3 different actually just spots. So let me draw the picture in 3-dimensional space. You have X, Y, Z axes, and the box created gravitational force mg, which is 480 pounds. That is vector W, and that also just attach the rope, and that rope is held by this 3 different actually spot on XY plane. That is P, Q, R. The P is 0, 2, 2, and Q is 0, 4, 0, and R is -2, 0, 0. So the 3 different points hold this point S, which also hold the box of 480 pounds. On that point S is 0, 2, -1. So in order to find the force exerted on the individual rope, we gotta actually just first estimate the vector. So number 1, weight on the point S is W. So that is the downward due to the gravity. That is downward force. So we gotta first actually just estimate the vector of force. So here that is 0, 0, 480 minus 480 pounds because it's downward. So with that, next one is first, let's take a look at the the vector U, and this is vector V, and this is vector Z. Okay, so let's just check the vector U. Vector U, now we actually think of the magnitude of vector U as force. And then we should actually find the direction of the vector u, which is vector sp. So that is sp over magnitude of sp. That is unit vector along the direction of sp. So that is same as unit vector. Now, that's just pretty straightforward because we know that the terminal point of those two vectors. So that is 2 minus 0, 0 minus 2, and 0 minus minus 1, divided by magnitude of the vector sp, that is 3. So that vector is force vector u times 2 over 3 minus 2 over 3 and 1 over 3. That's vector u. And number 3, vector v is the magnitude of vector v times normal vector sq. So it is magnitude of vector v times sq over sq. Same thing, that force vector v times 0 minus 0, 4 minus 2, 0 minus minus 1 over square root of 5. That is magnitude of sq, vector sq. So that is force vector v along the sq times 0 in the direction normal vector sq, 2 over square root of 5, 1 over square root of 5. And now number 4, vector z is the force vector z times unit vector sr. That is force vector z, magnitude of z times sr over magnitude of sr. That's a unit vector, so that is the force magnitude of force vector g times minus 2 minus 0 for x component, 0 minus 2 for y component, 0 minus 1 over 3. That's the magnitude of SR, the vector of SR. So that leads to the next vector, this vector, z times minus 2 over 3 minus 2 over 3 and 1 over 3. So in order to stay in that, equilibrium out of these forces, that the summation of all those forces should be equal to 0. Because if there's a net force, total force is non-zero, then there's also acceleration is not equal. So that creates the motion of box. Then that indicating that the system non-equilibrium. So that means in order to stay at equilibrium of the whole system, the net force, the total system force F net, which is force vector U plus force vector V, force vector Z, force vector W should be all that should be the equal 0. So there's no finite amount of force stay on the system. So that is condition for equilibrium. That means box stay at rest, stationary. So now this condition actually can be re-expressed with the u v z vector. And u plus g, v plus g vector equals minus w vector. So with that, we can combine, we can just actually estimate the u v z out of that is 3 and the 4 equation 4 condition. So with that idea, we can estimate the forces exerted or tensions exerted on the each rope, extending to the fixing point. Okay, so from that you can actually just combine x, y, z component altogether out of u, v, z vectors, force vectors. So the for x component, the if you add all x component out of 3 vectors, then that should be 2 over 3 u minus 0 times v minus plus actually 2 over 3 the z vector. And number 2, y component, that is minus 2 over 3 u plus 2 over square root of 5 v minus 2 over 3 g equals 0. And number 3, z component, that is minus 1 over 3 u vector plus 1 over square root of 5 the v vector plus 1 over 3 the g vector equals 480, because that is this 3 vector is the 3 component is the ones for the w vector, actually minus w. So from that, now you have 3 unknown variables, but you also have 3 equations. So based on the linear algebra, you can actually just drive the numbers for the u, v, z vectors. So from that, u vector, the force along the SP, the point P, the force exerted on the rope along the SP is 360 pound, and the v vector should be 536.7 pound, and the z vector should be the 360 pound. So those, if this 3 different number of forces apply to the rope attached to the point S to the 3 different points, then that point S should be the equilibrium, and then no movement, nothing, and just stay at last. That's all vectorial summation out of these 3 vectors should be same as w vector, which make that attached box stay at last and no movement, nothing. So no force applied. Okay, that's the answer for this question.